Back in the 1980s, we had the best TV commercials. Here in the United States, there's a hamburger restaurant called Wendy's. And back then, the commercials were all about this woman going around saying, "Where's the beef?" And she was trying to find out where the beef was in the hamburger. Well, even though it might have been a funny commercial back then, nowadays what we want to know is where's that mobile phone? Or where's that laptop? Or where is that barcode scanner or some other device we want to locate? Well, there are a lot of methods that we can use for locationing within wireless networks, Wi-Fi and otherwise. And today, we have one of the best experts in the world on wireless, Jerome Henry, with us. And he's going to be talking to us in this session about wireless locationing.
Hello, everyone. Welcome to this session on indoor location. My name is Jerome Henry. I'm a principal engineer at Cisco Systems and CWNU45. And I've been working a lot on indoor location for the last few years. So I wanted to give you an insight into what's happening there at the IEEE and what's happening there at the Wi-Fi Alliance. So indoor location is a particular topic because it's been fairly quiet maybe in your world for the last few years, but things are brewing here. So I wanted to give you what happens. So indoor location is an extension from outdoor location. And I'm not saying that outdoor location has been solved, but we're getting there. And it's been solved because we've been combining a lot of technologies, GPS plus, cell triangulation plus depth reckoning, the device sensor, etc. So it's a combination outside of multiple techniques that slowly brings us to have more and more places on the earth where we have location down to an accuracy of about 1 meter. So we know that indoor is likely to be the same. We'll have to have multiple technologies to be able to give you a high accuracy location. And the accuracy you want will also drive what kind of technology you'll be using. So if you're just looking at building level, Wi-Fi is probably very sufficient. And that's what we had for last 20 years. And then you can get a bit closer to get what we call the zone level. And that's something, again, we have for a long time now. But we'll also have a better a type of technology sets, put up, for example, BLE, etc. And then if you want to go very narrow down to 1 meter accuracy or less, you'll need, again, new technologies like ultra-wideband or something else. So FTM has been trying to get into this zone area where you can get an accuracy down to a few meters if you can. The difficulty in indoor location is that it's different from outdoor in the terms of use cases. Outdoor, it's you with your phone, you want to know where you are. There is no, GPS satellite needing to know where you are, although there is all this urban legend about, being tracked by the government, and that may happen. But the use case, for the commercial usage of the technology is clients, blue dots on the client device. But indoor, it's different. You have that use case too, but you also have, very legitimate use case where the infrastructure needs to have understanding of the population of Wi-Fi devices for analytics purposes, scaling the cell AP count, etc., or asset location tracking. You want to know where this blood pump is, in the hospital. So because we have those two types of approaches in use case, for the longest time, Wi-Fi has been failing to get a good location solution because it takes two to tango. And one use case for the station doesn't match the use case requirement for the infrastructure. So getting the two together has been difficult, especially because we need signal. We need to have a system where there is a sort of a mutual understanding of what the other side needs. So you can have, for example, a station finding its location just by hearing the GPS style, the access point signals, but then it needs to know where the access points are. So the access point need to cooperate there. Or the access point could be cooperating with the station to exchange frames, and then you could have a more dynamic structure. But then why would the infrastructure do that? Same thing, if the infra needs to know where the stations are, maybe it can just listen to the station signal. That's what we've been doing again for a long time. But then, there is no cooperation from the station. If the station goes to sleep or rotates its MAC address, then, the connection is lost. So there could be also here some connection sharing where the two work together. So what FTM tried to do is to try to improve those technologies you see here to get this presence and zone type of efficiency with having both sides exchange frames. So we are right in the middle of this, high accuracy location, just general zone location. And we are in this realm where we say, it takes two to tango. Let's have the access point and the station cooperate together to try to give each other some information. But that means that we need to have both sides do something. In FTM, the way a structure works is that you have a station that needs to find its location. Typically, it's the station, the client station. We call it the initiating station, ISTAY. And then it will try to range against what we call a responding station. That's going to be typically an access point. It has to be something fixed, something that doesn't move. It's going to range against it. And then from that range, it's going to understand its distance to that reference point, to the R state. And then what the R state is going to do is to send down to that station its own location, its GPS location. And because it does that, the station, the ISTAY, ranging against multiple R states, is going to be able to know its reference location, distance to those points, and the position of those points, and therefore its own location. So in 2011-2012, there was a first protocol called timing measurements, where a station could exchange with its access points. But the goal here was just to exchange time, clock information. And the goal there was to use, sort of a TSN, no, it's not a sort of, it's TSN time sensitive networking structure so that the clock could be synchronized between the station and the client. In 2016, the 802.11 standards, realized that, hey, we could do more than just timing. We could also use that for location. So they expanded this TM into FTM, fine timing measurement, which is what you see on the screen. And at the beginning of the process, your station, the ISTAY, is going to query an R state that announces in its beacon probe responses that it does FTM, that it wants to do ranging. And it's going to propose a certain number of values. I'll show you more in one slide. And then the R state is going to respond saying, yeah, I'm going to agree with those values for the exchange or override them. And then in a certain number of bursts, at the beginning of each burst, the R state, the AP, is going to send a message at time T1. And then that message is going to be received by the station at time T2. The ISTAY is going to acknowledge the message and sending the ACK at T3, and that T3 is going to reach the R state back at T4. So you have this ping pong, each of the two having 2 times. And then in the next FTM exchange, the R state is going to send to the ISTAY its T1 and T4 value for the previous one. So now the ISTAY has all 4 timers for the previous exchange. So by using the equation you see, basically the time of flight is the time divided by 2 times the speed of light. The ISTAY can find its distance to the access point. And then if it can query along for the access point, what we call LCI, location configuration information, that will allow it to know what is the geoposition of the AP. And then, from doing that with a few access points, it doesn't need to be associated, by the way. So it can do that for any access point that supports that in the environment. The ISTAY will end up finding its own position. So that's the logic. The burst of the exchange, as we're CWNP here, let's look at the frame a little bit, right? It's an action frame, so of course type 13, and subtype 20 and 21 for the request and the response. And the negotiation that we mentioned in the previous slide takes into account a few parameters, how many bursts you want to do, how long are these bursts, how many microseconds or milliseconds between these bursts. Within one burst, how many frames? What is the interval between the frames? Do you want them all at the beginning of the burst and then silent so you can do something else? Do you want to spread them across the burst? You can exchange a lot of parameters that allow you to fine-tune the way you're going to range. And the reason why you want to do that is because the cell may be busy, you may be ranging against multiple APs, you may be having a buffer to empty, so you may want to organize the transmission and the exchange based on your own ability to be able to run those exchanges in good conditions. Okay, so that's a capture in Wireshark. And if you're interested in looking more into those captures, just reach out to me. I'll be very happy to share with you some FTM frames. Not all access points support that. I'll tell you more about that in a few slides. But you see here on the left side, that's a request, initial request, where the station is sending its parameters, requested parameters. And then what you see on the right side is the first frame from the access point after, within a burst, where it sends, the response. That's what we call the Wireshark calls the response, but it's the FTM request frame. And then you have the time the T1 and T4 values for that frame. Here we are just starting. That's why you just have the T1 value. So that's the logic. Before we move on, let's be clear on something important, which is accuracy versus precision. What you want to get is good accuracy, and you want also to get good precision, but there are differences. Good precision means that when you do a sample, when you measure the distance, all the distances you're going to measure will be within the same small range of numbers. So here you see the icon at number 1. That's high precision. All the values you get are close to each other. But that's not accurate, because your real position is the red cross. So although one is fairly precise, which means that the channel itself is reliable, it is not accurate. So you get not very close to the real position. At the same time, the values could be accurate. That's what you get for 2, where you may have samples all over the place, so it may not be very precise. But when you average those samples, then you get something which is close to the real position. So therefore, it's very accurate. So what you want to have is both, right? If you can. High accuracy, so you get real position as much as you can, real range, but also high precision if you can, so you can trust that when you get a few samples, you have enough information to know where you are instead of having to collect a lot of samples. So with that in mind, let's look into why FTM is complicated and how it's challenging, and why it may be that you don't have it in your phone today and it may need a phone refresh. And here I'm going to go into physics. And for those of you who have done signal processing, please pardon me, I'm going to happily mix the time domain and the frequency domain. But I'm not going to go into the Nyquist theorem, etc. I just want this point to be clear into what happens in the chipset, in the system, when you want to do that kind of a measurement. And what is difficult is it's about sampling. Imagine that you have to sample a sine wave. You have that wave that goes up and down, and you want to know when it goes up and when it goes down. You understand that if you want to know that span, you have to sample at least somewhere by the bottom and somewhere by the top. So for each frequency length, you have to sample about twice. So that means that we say you have to sample at twice the bandwidth. So if you have a system where you're going to be measuring a signal over, say, 20 megahertz, and if you have about 1 million samples per megahertz over the 20 megahertz, that means that if you want to have a good understanding of this sine wave, you're going to have to be sampling about 40 million times per second, twice, per unit of hertz, basically. A hertz, is 1 cycle, so twice per unit of cycle that you expect per second. And the reason why I'm saying this is because Wi-Fi cards are designed that way. You want to understand those wavy things coming to you so that you can know if they contain 1 or 0s. So that means that because the frequency at which and the channel width at which the signal is coming to you, your cards have been manufactured with this ability to sample the matching twice of a bandwidth amount of time. So that is very important to us, because it means that this is not something you can configure, right? It's built into the chipsets, and it's a physical thing. You can sample more often, of course, but that's going to cost you a lot more to manufacture the chips because it requires more sensitivity, as we say. So your card is doing this by structure, by design. But if you sample every 40 million times per second for a 20 megahertz signal, that means that on average across this 20 megahertz wide signal, you're going to sample once every 25 nanoseconds. So you just do the math, right? 1 second divided by 40 million samples, that gives you 25 nanoseconds. The thing is that during that time, the 25 nanoseconds, light is going to have traveled about 30 centimeters. So that means that if you are sampling that way over 20 megahertz per second, your goal here is not to know if it's a 0 or 1, but you want to know when the frame arrived to you, because you want to measure the time of flight. So you want to know when exactly the frame is leaving the antenna. That's something you can timestamp, but you want to know exactly when it's receiving on your side, when the antenna is receiving on your side. And if your sampling of that signal on the antenna is once every 25 nanoseconds, well, that means that if you sample now and then you sample in 25 nanoseconds and there is energy at that time, you know that the energy has started arriving to you between time 0 and time 25 nanoseconds. So what kind of accuracy can you get there? Well, depends on how you sample it, but if you receive it any time before last time you sampled there was no energy, now there is energy. It arrived somewhere in between. You can do a sort of simple mean and say, well, probably it arrived by mid time somewhere around 12.5 milliseconds, but 12.5 nanoseconds of inaccuracy is 3.75 meters at speed of light, which means that because of the way your antenna is set, because of the way your chipset is set, by sampling every 25 nanoseconds, you cannot get a better accuracy at 20 meters than 3.75 meters, because that's half the sampling rate at which you're going. So that's the best guess you can take. So that means that you cannot get better than that. And even worse than that, most of the time we'll tell you about the rise time, we'll tell you about efficiency of the filter, etc., which means that it's even less than that in practice in most chipsets, unless you put a lot of money again in your chipsets. So that makes that you have a physical limit in the amount of accuracy you can get based on the type of signal you're receiving and the frequency at which you're sampling. But also what it means to us, which is very important, is that if you are doing that thing over 20 megahertz because you have 40 million samples, you sample over 25 nanosecond per sample. But if you increase your channel to 40 megahertz because you have to do the same thing twice now, you're going to sample twice as much, the first 20, the next 20, and all of these have to be done in the same second. So you have to go twice as fast, so to speak, which means that as you increase the bandwidth, the amount of time between one sample and the next decreases because you have to sample a larger signal now, so you have to go faster. So that means that the accuracy you'll get will be larger as the bandwidth you're using increases. That's important because, as you know, we have 20, 40, 80, 160 megahertz. And there are technologies like ultra wideband that even send at 500 megahertz. And those give you very high accuracy, not because they're better technologies, just because the signal is wide. So they're sampling very often. So they give you something crazy like a few centimeters. So how do you get better than that? Can you? Well, you could think you can, right? So if you are getting a sample now and a sample in 25 nanoseconds, and you say, well, my signal probably arrived in the middle, you should take, this mid-T and say, well, my accuracy is going to be 3.75 meters because, the signal arrived between 0 and 25 nanoseconds, which means roughly probably at 12.5, right? Well, no, not right. What you want to do is not pick up the average. You want to pick up the best one. And that's why you have multiple exchanges in the burst. You want to have multiple exchanges. And instead of doing this left thing that you see here, which is a mean, you take the average value between all the ones you sampled. Some of them will arrive right after 0. So you will get it 25 milliseconds later. Some of them will arrive right before 25 nanoseconds, and you'll get a signal right there. What that does is that when you measure this T1 and T4, you will have a sort of a shifting value which depends on your sampling rate and when you receive that signal. So what you want to do there, instead of taking the mean 12.5 average, you don't do that. You just take the shortest one. So you take many samples, and as you take all these samples, you take the smallest. That's the logic. And that makes that not only you're likely to be receiving the shortest sampling, but also you're also likely to be receiving the signal which is most likely to be line of sight instead of having something which may be reflection. So it still doesn't solve everything, right? Because multipath may still make that the strongest signal that you will get may be a reflection. So what you'll be getting may not be the direct line of sight. There's also something we call the rise time, which is even when you do that sampling at 25 nanosecond, it takes you some time for the circuit to be excited enough to understand that there is energy beyond the noise here. So that rise time also takes its toll on the accuracy you can get. And of course, if that rise time is reached for the multipath signal and not the line of sight signal, you never hear the line of sight signal because you're getting just the wrong reflection. But that logic of taking the smallest sample is pretty much where you want to be. So I'm saying all this to say it took a long time for Wi-Fi to be able to produce chipsets that were having a channel wide enough to be able to have good accuracy, and that were having a clock good enough to take that sampling and timestamp the time at which you receive the frame with a good accuracy. So what do we get? Well, we started from very poor, and you see here what we had back in the 2015 era. It's probably very difficult to see on the slide, but what you see at the top is what you do not want to see. All the blue dots are the samples you're getting. So you see that the numbers you're getting are all over the map. It's a wide range. And also it's not mapping the red line, which is the real position you were at. So that was fairly poor. And the graph at the bottom is what we call the CDF, which is the position error you get. And you see it's fairly sloppy. You know, the scale, you get 90% accuracy somewhere around 4 meters, which means that you get about a 4-meter accuracy. You know, you're within 4 meters of the real position 90% of the time. That is not great. But working, you know, with the industry, we got much better. What you see today is what you see on the right side, where we have an accuracy. You see it's much better. The distribution on the left, on the top left, is close to the real position, and also the distribution of the samples you get is very close to your real position. So it gives you, you know, much smaller range. So there is much better fidelity in your recording of the values. And also, as you see on the right side, the CDF now, instead of being this ugly curve going straight, is giving you 90% around 1 point something meters, 1.5 meters at 80 megahertz. So that means that you have a ranging value that is 90% of the time within 1.5 meters of the real value at 80 megahertz. What you see at the bottom is an experiment we did with Intel Labs, where the blue line is the real position of a robot, you know, driving across a floor, you know, a multiple paths, you know, along a floor of a building, and then at the same time it was ranging against access points, and the blue dots are the ranging values. So you see there are some values, you know, here and there that are a bit across because we're going behind walls, you know, suddenly getting line of sight and so on. But you know, overall there is a good match between the position that we compute, the range we compute, and the real position of the robot. So this is important for the ranging, but for location is different, right? Because here we're ranging to the access point, and then once you range to the access point, you're going to combine the ranging from two multiple access points to get a performance about the location. So location is going to compensate the errors a little bit of the errors you get to each access point. So when we started back in 2015, that's what you see on the left side. Each blue dot is the position of a map, and you see the real position you had before is what you see at the bottom, where you know the red cross is the real position, the green circle is what you computed. So you see very often you were like way off depending on where you were in the building, simply because you know you would be walking behind a wall and suddenly your signal would be inaccurate. You would be behind an obstacle and going back in 3 lights, so you have different samples, and it would be very inaccurate as well. But today what we get is about this. So at the bottom you see, I don't know if you can see the difference between the green circles and the orange, red crosses, because you know they are within a few centimeters of each other. Again, our accuracy to the ranging is about 1.5 to 1.7 meters at 80 megahertz, about 2.5 at 40, about 4 at 20 megahertz. But once we do that with multiple access points, of course, you know, we're going to compensate the error from one direction with the other to get a position right in the middle. So the real position you'll get will be better than the ranging accuracy you get. And what you see on the upper right side is that path where the blue line is the real path, and the orange is the computed position of the device as it moves. And you see there is on the corner an area where there is no AP anymore, so the thing is a bit confused. But anywhere else in the building, you get an accuracy which is between 1 point something meters and down to about less than 1 meter. That means that with that system, you can see on your phone your position, and it's accurate down to 1 meter. So that's the state of research there. Where we know that? Well, FTM in 2016 was released. It hasn't been implemented much. There has been a Wi-Fi Alliance certification in 2017 called Location R1. The implementation support is very small. And the reason is because, multiple things. One, FTM itself is a bit noisy. You can have a lot of samples. Plus, there is not a lot of benefit for the access points. The station gets its DI state, right? It gets its location, but the responding station, the infrastructure, doesn't get anything. It gets noise, right? Airtime consumed because it's doing that thing. Then people say, well, that's the access point is not working as well as the others because I cannot get as much throughput. Yeah, because the AP is busy helping you finding where you are. So the adoption has been small. But since in 8.2.11, a working group called AZ has been working, and it's going to be published probably mid 2021 to improve things in a few ways. One is supporting for MIMO, so you can have multiple devices trying at the same time. Another one is what we call passive mode, where just the APs talk to each other. The stations are just listening, so you can have an infinite number of stations listening and finding their way without having this exchange, so it's less noisy. There's also what we call the LMR feedback, where the station can return back its location to the access point, which is useful for asset tracking in enterprise environments. This is negotiated, which means that in public environments you can stay private, but when you get in enterprise environments, you can have a profile to exchange back so that we know where you are, etc. There's also a security improvement where you can use that feature to know if you're close to a door, for example, and have a sort of a physical protection of the connection so that nobody can spoof your signal to the door and pretend to be you near the door. That's something that happened back in the days of ultra wideband, where people were emulating these fob door openers for your cars by capturing the signal from your key and relaying it to the car, making the car think that you were closed and opening the door and stealing, of course, the car while you were the car parked outside where you were sleeping in the house, just by relaying the traffic from your fob on the table through the window and to the car. So to avoid that in FTM, we have the security, physical security, where you cannot do that spoofing. So that's the work at the IEEE. So in about a year, we'll have all these features coming out. And because of that, a lot of excitement is coming back into the industry, so much so that the Wi-Fi Alliance has started a new revision of the protocol certification, which is called Location R2, where we have a much more involvement of vendors, access point vendors and client vendors. Today, you will, if you look up on Google FTM support, you will find a few sites that list the devices that support FTM. It's not many of them, but many Broadcom and Qualcomm chipsets support FTM silently because the operating system doesn't activate it. Android supports it natively now. iPhone iOS doesn't yet. Windows not yet, but there are Windows implementation, the Linux implementations. On the access point, you start seeing new vendors, some vendors starting to support this system, some home vendors and some enterprise vendors. So it's a technology that keeps brewing, and that's why I wanted to bring that to your attention, because it's very likely that within the next year, in 2021, you'll start hearing more and more about FTM as being the new thing that people want to talk about. And I wanted you to have the prime idea about, that technology, which will make that maybe in a year and a half or 2 years, you will have natively in your operating system on your device, a system which will allow you to have an accurate blue dot inside. All right, let me stop there and pause for live questions.
All right, Jerome, welcome. We've got a nice section here where we can do some Q&A for the presentation that you gave. First of all, how are you today?
Doing well. Thank you, Tom, for organizing this event. It went well. I know I've been watching all the sessions and I learned a ton of stuff. So this is super entertaining, super useful.
Excellent. And it's exciting to have you back. I don't think we've had you at one of our conferences now for quite a few years, have we?
Yeah, last time was BC, right? Before COVID, but it feels like so much before. It feels million years ago. So I'm very happy to be back. And apologies. It seems that I had a glitch in the description of this session, describing the next one, which is tomorrow about rate adaptation algorithm. But yeah, I'm very happy to be back too.
Oh, I got you. No problem. No problem whatsoever. We'll get that worked out. Well, we do have a couple of questions that have come in, so let's make sure that we address as many as we can in the minute and a half or so that we have left. So with 3GPP release 16 and upcoming 17, indoor location accuracy should be greatly improved, they say. Since 5G will require a lot of indoor microcell build out, why shouldn't LBS be done via LTE 5G? What do you think?
I think we could. I think you could use 5G. You could use ultra wideband. The only issue there is that you have to build an overlay. This system doesn't exist today in your networks. You have to bring all these small cells. If it's ultra wideband, you have to build all these overlays. So it costs just more money. But whereas Wi-Fi, you probably have Wi-Fi APs today, so you can use them to locate. So it's a question of cost to efficiency.
Sure. Okay. Good point. The next question, what happened with the location enhancements in the 802.11 MC rollout?
Yeah, thank you. And somebody was talking about that in the Q&A and the chat. In 2016, that was the third revision of their standards. So people say it's 802.11 maintenance C ABC. So a lot of people say, oh, they designed 11MC as location. it's a 4,500 page long document. So in there are 2 pages on FTM, fine timing measurements, and some people call it RTT, round trip time. None of that is accurate. It's not MC, it's fine timing measurement in the thread vision of the standard. And it's not round trip time because you do account for the travel through the station. So I think we're talking about the same thing. It's just, the vocabulary that's a little bit different. So that's what it is. But it's going to be greatly enhanced with even AZ or AZ in a few years.
Absolutely. All right. Well, great. We appreciate you taking the time to address the audience directly and looking forward to your presentation tomorrow as well. And so until then, Jerome, thanks a lot for joining us.
Thank you, Tom. Thank you, everyone. Talk to you tomorrow and looking forward for the next session.
All right. Take care.